Hello everyone, my name is Minko Gechev. I'm working on Angular at Google. Today in this presentation I would want to look into some very shared problems across teams with a lot of engineers who are maintaining large code bases. So if your team is not consisting of like 20 or more people and the system that you're building doesn't have hundreds of thousands of lines of code, the individual areas that we're going to touch on today might not be directly applicable to you. But I'm hoping that the content is still going to be interesting. All right, let us get started with performance first. I've pretty much never heard from anyone ever that their productions are small enough. I've never heard anyone being completely satisfied with their application's load time performance. And this is especially true with your applications growing and scaling over time. And while usually folks are blaming the framework for that, and well, they are correct to blame it for small applications. When your app is small, the framework is taking most of your final bundles. You have a little bit of application code, but the majority of what you're shipping to the browser of your end users is the actual framework. With your application growing over time, however, your application code increases a little bit and you start adding third-party dependencies. With the framework primarily staying with a constant size. Over time, you keep adding dependencies, and at a certain point, these dependencies pretty much get out of control. They're taking the majority of your bundle, even more than your application code. But the framework size is still constant, and it is taking a small portion of your production JavaScript. The usual way to explore this and to optimize such applications is to pretty much reduce the number of third-party dependencies you use, delay them, for example, add them in lazy loaded modules, or just replace them with their more compact alternatives. But in order to see this overall picture, you can use tools such as Source Map Explorer that are going to help you identify what actually you have within your application bundles and give you more insights on how you can optimize your application from there on. Source Map Explorer is a tool very similar to Webpack Bundle Analyzer. It, however, sometimes produces more accurate results, since it is looking directly at your production output, instead of analyzing the stats coming from the Webpack internals. To use Source Map Explorer with Angular, you pretty much need to open your angular.json file, enable source maps for your production environment. Right after that, run ngbuild --prot, and in your dist directory, run Source Map Explorer to see the layout of your main bundle here. Source Map Explorer is not something Angular specific. You can use it with any framework or CLI tool out there as soon as it produces source map for the final application bundles. I recently ran Source Map Explorer on top of a not too large actually research project for finding out an antiviral for COVID. They were using Angular and some third-party libraries for visualization of 3D models. When I run Source Map Explorer, I noticed that these third-party modules, well, not only the visualizer, but also some modules outside of Angular core that we're shipping as part of the Angular platform, were taking the majority of the final output. So we have this large third-party dependency, we have material, we have some pieces of the CDK, we have the raw alter animations, we have HTML, ng5 slider that is taking about 5.3%, and so on and so forth. But the framework itself is taking a pretty small portion of the overall bundle, which is probably around 3.2% or so. Yeah, about 3%. This is something that there is a book called The Pragmatic Programmer that I read when I was in college. And there is the story of the broken window. So the broken window experiment was done by folks from the academia a couple of decades ago. They took a car and they placed it into a neighborhood in New York City which has a very large crime rate. Well, the expected happened. This car was completely smashed. Everything from the inside was stolen, and all the windows are broken, and it was pretty much destroyed. They took another car and they left it in a very good neighborhood in Palo Alto, California. Palo Alto is a city which is south from San Francisco. It is in the Stanford area. Stanford is pretty much inside of it. And it is pretty safe. If you have been there, you know that it is sunny most of the time, people are friendly, and the crime rate is pretty low. They left the car there and, everything was normal, as expected. However, they broke one window of the car. The next time they went to see their vehicle, they noticed that the entire car was smashed and trashed pretty much the same way that it was in the in the neighborhood in New York City with large crime rate. So I'm only telling you the story because there is a similar concept in software engineering as well. The broken window. This pretty much refers to having a project in which you're keeping everything very tidy and clean. However, at a certain point, you'll start adding a third-party dependency that, let's say, is not too well tree-shakeable. This leads to some small performance regression. Over time, you add another dependency and you think about yourself, probably I shouldn't do that. But, I have already this first dependency that is adding some extra weight anyway, so maybe I should. And this pretty much continues. This also relates to the boiling frog. So you break one window and from there you experience a lot of regressions. Especially in large projects, which span across hundreds of thousands of lines of code, it could be even more challenging detecting such broken windows, especially in large teams. So that is why there are a couple of techniques to catch such broken windows early on. One of them is introducing performance budgets. The performance budgets set some constraints on top of your applications. For example, you can constrain how large your bundles could be. And in fact, this is something that we're already supporting by default in the Angular CLI. There are already established third-party modules that allow you to do that with other frameworks as well. And there you can set a constraint on top of your resource sizes. For example, you can say that you don't want your bundles, your main bundle, let's say, or the bundles that your users are going to load on first, you don't want them to be bigger than 300 kilobytes. You can set this restriction as part of your build pipeline in the CI. So if on some reason the size of any of your third-party dependencies increases, your CI is going to fail and you're going to notice this performance regression. Another technique that you can use is adding performance profiling as part of your CI. Some time back, the Lighthouse team introduced Lighthouse CI, which allows you to do different performance measurements and even accessibility and best practices ones, and add them as part of your CI. So if you notice a regression above certain threshold for, let's say, your performance, your build is going to fail and you're going to notice that as part of the pull request that came in, so that you can see what went wrong, fix it, and prevent such broken windows and regressions. That was the first topic that we described today. Now let us talk a little bit about structure. In terms of application level structure, there are different areas and different levels of granularity that we can look at. For example, selector collisions is one such example, where different folks and different frameworks are solving in different ways. It was particularly frequently happening in the very early days of AngularJS or web components. Now with Angular, we have different ways for handling it. We have also different directory structure techniques that we can use, and sometimes we have leaking styles. I'm not going to dig too much in depth in leaking styles because, most frameworks nowadays, most modern frameworks are already providing different scoping of such styles. Angular does this pretty much since the beginning by using emulated view encapsulation or shadow DOM. Now let us talk about selector collisions. But before that, I want to talk a little bit about scoping in programming languages. Pretty much the scoping is a binding where we're associating name with a particular entity. In computer software programming, we have variety of different scopes, variety of different types of scoping. In fact, we have primarily lexical scoping and dynamic scoping. Lexical scoping is something that you're used to from writing your day-to-day programs. You have functional lexical scope, let's say, by declaring variables with var in JavaScript, or you have block lexical scoping by declaring variables with const and let. In Angular, however, we have our own type of scoping. For example, if we look at this app component, we can notice that we have app dropdown. But just looking at the app component itself, we cannot be sure where this app dropdown is coming from. And we can very easily have app dropdown collide with any other selector of any other component somewhere outside of our application, for example, coming from a third-party module. In this case, however, having the dropdown component right next to the app component, we can notice that, well, probably the selector from the dropdown is matching the app component here, the one that is used in the app component right here. So in Angular, we have two different ways for handling selector collisions. The first one is that we're adding a small prefix. This is more of a convention that we introduced in the very early days of the Angular style guide, where we're recommending to prefix the selectors of your components with app. But we also have NgModules. NgModules are determining the dynamic scope into which Angular will compile collections of components. So let us go back to the previous slide. Why I'm saying dynamic scope? This is different from the lexical scope that you're used to in your day-to-day work as a JavaScript or TypeScript developer. Here we have app dropdown. We have already bound a particular name. We have already this name, but we haven't bound a particular component to it. To bind a component, we need to add the app components to an NgModule, which has declaration of the app dropdown component, of a component with the app dropdown selector. So this way we're mapping or like binding the already existing name with a component that is defined as part of the same NgModule. This way we're very easily preventing selector collisions since, well, we need to add a component associated with a particular selector to the given NgModule to have this corresponding binding. These selectors are not global and they cannot cause collisions easily. All right, so that was about selectors. As I mentioned, there are different frameworks that are solving this problem in different ways. In React, well, the React folks are taking advantage of the lexical scope of JavaScript, so they don't have to think about implementing their own scoping, such as the one we have in Angular with NgModules. On the other side, things that are much more dynamic and hard to optimize at build time. So, well, this has its own pros and cons, of course. It has its own trade-offs as anything in software engineering. All right, so directory structure. When I started originally building applications, me and my colleagues were usually structuring the apps around the logical units, the logical building blocks of the applications that we were growing. So we had components, directives, pipes, services, and so on and so forth. However, over time, we went into a more conceptually oriented directory structure, which got much more intuitive because we were structuring the source code around the individual features of the app. This was making the overall project much easier to read. Even as a beginner to this particular system, especially large-scale system, you can very easily get your way around it by looking at the names of the individual features or directories that match to features and parts of your app. So that is why, well, in the Angular style guide particularly, we're recommending the more conceptually oriented way to structure your apps. Another thing around directory structure is component reuse. In most applications that I have seen, folks have a variety of different repositories where they have, let's say, something like micro frontends. They have their individual applications in different repositories. They potentially have different shared components that are published as separate packages and live in separate repositories as well. But let us see how we can promote a certain component to such reusable package inside of the entire application or subpart of it. So let's suppose that this is our directory structure. We have the root directory of our project at top, and we have two subdirectories. First, let us suppose that we have this component here, this directory here that uses particular set of components. We also notice that the sibling directory is using the same set of components. So what we could do in this case is promote the set of components into shared set of components or a reusable library within this part of the application. If we start using this library across another directory which is part of a different component subtree, we can promote it again and move it to the top. And this is how we very naturally evolve to a monorepository. We can just take the component library and put it into a sibling directory to our project. This is generally going to simplify communication and simplify reuse, because we're going to have our component library as just another directory inside of our repository. So in order to reuse components, we just need to import them. We don't need to wait for the components team to publish them. We don't have all these boilerplates. We can very easily reuse infrastructure as well, since both our project and the component library, they can be built by the same CI. It is very easy to integration test them, and we have this single version policy, which is, well, one of the biggest struggles that I have observed in large code bases. Imagine you have a large organization with many different projects. I have talked to quite a few organizations in this scale over the past few years. All of them depend on Angular in my particular case. And the challenge there is how to update your applications to the latest version of the framework, having a component library. Because the component library depends on a particular version of Angular, but the individual projects, which are not inside of a monorepo but inside of multiple repositories, they depend on their own different versions of the framework. So the challenge comes in here. How the component library can support all the different versions of Angular that the individual projects depend on. The usual way to solve this problem is by introducing a monorepo and a single version policy. This way, all the different projects within the organization are going to rely onto a single version of Angular, which is going to be somewhere defined in a top-level package.js. And we're also going to have our component library that depends on the same version of the framework. Next, I want to spend some time talking about communication, pretty much type checking. Type checking applies across our entire stack. We have type checking inside of our templates, inside of our source code, but it is very critical to have it across our entire stack as well, to have a statically typed communication protocol within our frontend and backend. There are different solutions that are helping with this, such as Swagger, GraphQL, Protos, etc. If we have a monorepo, we can very easily share this schema for statically typed communication across our two different nodes. And in a monorepository, we can also really easily test this. For example, if our schema changes, this means that probably our backend has changed certain endpoints, which means that we need to reflect this into the frontend. And if our CI fails because of that, we know that we need to do something about it. We need to do something in order to align these two different components. Golden files is another approach that we have been using in Angular for a while. With golden files, we are verifying that we're not breaking the public API of reusable libraries. In our case, this is Angular, our components, and so on and so forth. Golden files are just the type definitions of our public reusable libraries, and every time when we build the framework, we're generating these type definitions and comparing them with their previous version. So if something has changed, this means that we have changed the public API. and we need to revert this if it was unintentional. The runtime verification, here I'm referring to having end-to-end tests across the front end and the back end. And here the biggest challenge that occurs in large orgs is build speed. The build speed could be a really large challenge at scale. Well, the build of an application of a customer that I talked to was taking a month to complete. Imagine that, a month to get your production build out. And this is a true story. So incremental builds you can achieve in the Angular ecosystem in a couple of different ways. Clearly, now you can use Webpack version 5, but this doesn't help you scale your build within your entire organization. It has persistent disk caching, which is primarily applicable only on your local development machine. However, you can use something like NX. NX allows you to split your application across different projects and libraries and have incremental compilation across all of them. This way you can even have cross-language dependencies. Some folks from the Angular community already developed adapters and built plugins for Go and for Python to be used inside of a NX workspace. You can have remote build execution and remote caching with NX so that you can reuse this remote cache within your entire different teams within your organization. And you can build a single package or a single library only once. A more granular approach that we have been using inside of our Mon repository inside of Google is Bazel. With Bazel, we have finer level of granularity, and we have one universal build system, which is more explicit compared to the approach of NX. So you're more descriptive into what is your dependency graph, but at the same time, you're getting hermeticity and a really powerful and fast build at scale. Bazel also has remote caching and remote build execution, so you can build your project only once. Cache it into the remote cache so that all your colleagues and the CI can reuse all the resources that you already produced as part of your original build. That is pretty much everything I had for you today. These were some of the challenges that you can face at scale. They are primarily oriented around build performance, application structure, load time performance of your app, communication, and independent deployability. Thank you very much for listening to my talk. If you have any questions, feel free to reach out to me on Twitter. Bye-bye.